Welcome back to The Explainer. I'm your host, and this deep dive is brought to you by the chief engineers over at Forge College. Today, we're grabbing our hard hats, rolling out the blueprints, and stepping straight into the EVM engine room. We are going to look at exactly how opcodes operate at runtime, and trust me, the strict execution constraints governing them are absolutely fascinating. Now, I know what you might be thinking. Wait a minute. Didn't we just build Solana AI tools? And if you caught our last explainer, yeah, we absolutely did. We were playing around with that shiny, futuristic, lightning-fast AI tooling. But today, we're pivoting. We're swapping out that sleek chrome for the gritty, strict, unforgiving mechanical gears of the Ethereum virtual machine. It is time to get our hands dirty with raw bytecode mechanics. So here is the blueprint for today's factory tour. We're going to start right in the EVM engine room, then look at stack framing and rules, dig into gas accounting, compare memory with persistent storage, identify some real-world execution traps, and finally, we'll watch the whole machine in motion with the fetch-decode-execute loop. Sound good? Let's get moving. All right, part 1, the EVM engine room. Strict rules, zero tolerance. Moving on to part 2, stock framing and rules, or as I like to picture it, the spring-loaded sorting tray. So I want you to imagine the EVM as this perfectly synchronized, incredibly rigid assembly line. The execution stack is our spring-loaded sorting tray, where all the immediate work actually happens. At the lowest level, every single opcode specifies a fixed stack effect. That's exactly how many 256-bit words it consumes, which we call pops, and how many it produces or pushes. Take the add opcode, for example. It explicitly pops 2 words off the top of the tray, adds them together, and pushes 1 word back down as the result. The EVM checks this before execution even starts. If there's only 1 item on that tray, the whole line halts, throwing a stack underflow exception immediately. Plus, the EVM enforces a strict maximum stock depth. If you hit that limit, the machine simply breaks. Which brings us to part 3, gas accounting rules. Welcome to the factory toll booth. Look, you can't run heavy machinery for free, right? And the EVM runs on gas. Gas accounting is this dynamic cost model that is woven right into the fabric of execution. Think of the EVM as a seriously penny-pinching auditor standing right next to the machine. Before an opcode even fires, this auditor checks your wallet and deducts a base upfront gas fee. But wait, it doesn't stop there. Certain operations incur ongoing dynamic runtime costs based on what they actually do. And if your gas runs out mid-operation, like say you're halfway through a massive calculation, the EVM immediately aborts the transaction with an out-of-gas error. It brutally reverts all your state changes, and the kicker, it keeps the gas you already spent. No refunds for failed labor. All right, part 4, memory versus persistent storage. Think of this as the workbench versus the titanium vault. Where the EVM stores its materials dramatically changes how it accounts for your costs. Volatile memory is basically your temporary workbench. It's call local. It starts out completely empty, and the second the execution finishes, that workbench is wiped totally clean. On the flip side, persistent storage is the contract's actual state. It's the titanium vault. Writing to this vault using operations like SSStore is incredibly expensive in terms of gas. Plus, it comes with these complex refund semantics that totally depend on whether you're changing a storage slot from 0 to non-zero or vice versa. It is a completely different beast. But hey, do not fall into the trap of thinking volatile memory is completely free. We have to talk about memory expansion. Memory is just a linear byte array, right? Well, the EVM actually charges you an expansion cost based on the highest byte index you access. And here is the real kicker. This cost is quadratic-ish. It has a fixed linear component, sure, but the per-word cost actually increases as the overall size grows. So if you sketch out data to sparse, scattered memory offsets, like say writing at index 0, then way out at index 1024, then back at 64, you're forcing the EVM to stretch your workbench out unnecessarily. Those intermediate expansions cost extra, and they can absolutely bankrupt your gas budget for literally no good reason. Let's look at part 5, real-world execution traps. What actually breaks the machine? So what goes wrong on the real-world factory floor? Well, compilers often turn high-level code into predictable but super dangerous patterns. Here are 3 major traps to always watch out for. First up, gas-inefficient storage loops. If you're running a loop that constantly uses sload to read and sstor to write back to the same state variable, you are paying heavy vault fees on every single iteration. A smart developer will just use a temporary memory variable and only write to storage once at the very end. Trop number 2, which we just covered, is sparse memory offset expansion. Writing non-contiguously will bankrupt you. Always try to reserve your final size up front and write into contiguous slots. And third, honestly the most painful one, late reverts wasting gas. Imagine paying top dollar to unlock the vault and store heavy materials, only for a later line of code to trigger a revert. Because the EVM treats calls atomically, a late revert undoes all those expensive storage rights, but the EVM still keeps the gas you paid to execute them. The lesson? Always do your cheap conditional checks first before you even think about doing expensive storage rights. Finally, part 6, the fetch-decode-execute loop, the machine in motion. Let's see how all of this builds into a complete cycle using the logic of a minimal Python stepper model. Check out this explicit opcode blueprint. The EVM maps every single byte to incredibly strict requirements. Byte 0x01 is add. It requires 2 stack items, pushes 1, and costs a base gas of 3. mstore, which is byte 0x52, takes 2 items, pushes 0, and costs 12 base gas, plus that tricky memory expansion we talked about. The machine literally just reads this metadata for every byte it processes over and over. And here is the exact 4-step heartbeat of the EVM's step function. Step 1, fetch the opcode at the current program counter. Step 2, decode it and check the stack depth. Are the preconditions actually met? Step 3, deduct the base gas up front. You gotta pay the toll. Step 4, execute the logic and calculate any dynamic costs, like that memory expansion. Do you notice what happens before execution even starts? The underflow checks and the upfront gas deduction. If step 2 or 3 fail, step 4 never, ever happens. Look, if you take away absolutely anything from this explainer today, let it be this. Treat stack effects and gas accounting as mandatory preconditions. When you trace opcodes, always annotate your stack deltas. Account for gas in 2 distinct phases, upfront and dynamic. By respecting these strict, highly mechanical rules, you're going to ensure your code survives the harsh reality of the EVM factory floor. So I'll leave you with this final thought. Are you ready to trace real bytecode? Because in the next explainer, we are going to apply this exact mental model and run step-by-step traces of compiled contracts. To get fully prepped for that, and to dive deeper into Ethereum fundamentals and a whole lot of other Web3 subjects, make sure you head over to Forge College. Thanks so much for joining me on this tour of the EVM engine room, brought to you by Forge College. I'll see you in the next explainer.